In this video, I'll be introducing vector spaces, dual vector spaces, and tensors. So the first thing I'll be introducing is the general vector space over a field. Let's say we have a field K under an addition plus and a multiplication dot. Then we say a vector space over this field K is going to be some set V, which I'll call the vector space, and operation circle plus, which I'll call vector addition, and another operation called circle dot, which I'll call scalar multiplication. Now, if my names didn't already give them enough meaning, this vector addition is going to take in two vectors, which are elements of the vector space. So I'll call some random element of a vector space a vector. So it takes in two vectors and outputs another vector. And scalar multiplication, as you might have guessed, will take in an element of the field K, and it will also take in an element of the vector space, and it will output another vector. So if we have two vectors V and W, I can vector add them. And if I have some element of the field A and some vector V, I can scalar multiply them. Now this is like on the real numbers. This is like real linear algebra, except on general fields. Now there's some conditions that are required for this to actually be called a vector space. The first one is that V under circle addition or vector addition is an abelian group. Two is the associativity of scalar multiplication. If I have A and I scalar multiply the quantity of B scalar multiply V, this is equal to A times B, and this is within the field, scalar multiply V. So we transitioned from scalar multiplication to multiplication within the field. That's why this is a necessary condition. Three is two types of distributive properties. The first kind is with vector addition. So if I have A scalar multiply V vector add W, this is going to be equal to A scalar multiply V vector add B scalar multiply W. So that's just simple distributive property. And the other type is with addition on the scalar. So if I have A plus B on the field, and I scalar multiply that with some vector V, this is going to be equal to A scalar multiply V vector add B scalar multiply V. So we transitioned from field addition to vector addition, which is sort of like the second property, except now with scalar multiplication and vector addition. All right, number 4 is that 1, the multiplicative identity of the field, scalar multiply any vector is just the vector itself. Now, a very basic example of a vector space over a field is the field itself. So it's the field under its own addition and its own multiplication. So if I wanted to add two vectors together, V vector add W, it's just V plus W. In scalar multiplication, A scalar multiply V is just field multiplication by the fact that it's just the field itself. And more generally than this, we can define a vector space on K to the n, which is K Cartesian product with itself n times. And we will give it an operation circle plus and circle multiply. And we just do pointwise addition and pointwise multiplication. So if I have K1 up until Kn, so these are all elements of the field and there's n components, we define the vector addition with another one, which I'll say K1 prime up until Kn prime is going to be equal to K1 plus K1 prime all the way up until Kn plus Kn prime. Just pointwise addition. And the same thing with scalar multiplication. If I wanted to do A scalar multiply some n component element of this vector space, this is going to be defined to be A times K1 all the way up until A times Kn. So it's just pointwise multiplication within the field. And this is a generalization of the vector space Rn to any general field. All right, so the next concept is of a basis. Now what a basis is a generalization of what you know of a basis from linear algebra. And this is just an extension of what you knew from real linear algebra. So we have a collection of vectors E alpha for alpha in some index set J. So this does not need to be finite. It can be any cardinality. So the first requirement for this collection is that it spans the entire vector space, which means that for every vector v in the vector space, there are two collections. One is a finite collection of these basis elements, so E alpha I for I equals 1 to n, and some finite collection of elements of the field, which I'll call K alpha I, and this is for I equals 1 to n. And the thing is that V is going to be equal to the sum from I equals 1 to n, and this is the circle plus sum. So this is the summation of K alpha I, an element of the field, scalar multiplying E alpha I, an element of the basis. Number two is that they are linearly independent. If I have a collection of elements of the field, Ki, this is a finite collection, then the summation from I equals 1 to n of Ki, scalar multiply E alpha I, these are elements of the basis, may only be equal to 0, so any linear combination of the basis elements is equal to the 0 vector, which is the additive identity under circle plus. So if this is ever equal to that 0 vector, that means that for every single index, Ki is equal to 0 on the field. A linear combination of the basis elements is 0, then all of the coefficients are 0. So this is spanning and linearly independent, which is what you knew as the requirements for a basis when you did real linear algebra. Now, using this first requirement for a basis, what we can write is any vector v as the summation from I equals 1 to n of v alpha I scalar multiply a basis element E alpha I. So this is just straight from the first condition, except we gave the components a name, v alpha I. Now you could also write this as the summation over alpha in J of v alpha scalar multiply E alpha, and you could just have it where v alpha is equal to 0 if alpha is not one of those alpha i's. So basically we can extend this definition of a finite sum to the entire basis, so we have this general summation, if we just require it that all of the components that were not in this finite sum are 0. However, I will more often use this version of it because it is finite, and finite things are better to work with. Now, a nice theorem is that any vector space has a basis. So that is a theorem. Every vector space you can find me, I can find a basis for it, assuming the axiom of choice. So if the axiom of choice is allowed, we can have a basis on any vector space. One of the uses of a basis is in classifying linear maps. But first of all, I have to define what a linear map is. So let's say I have a function phi between v under circle plus sub v and circle multiply sub v, and I send this into w under circle plus sub w and circle multiply sub w, and that both of these are vector spaces over the same field K. I will say it is linear, which I'll denote by a little tilde over the arrow, if phi of v plus in the domain w is equal to phi of v plus in the codomain phi of w. So the addition of two vectors in the domain is equal to the addition in the codomain of their images. It preserves this circle plus operation. And then same thing with scalar multiplication. It preserves it. If I do a scalar multiply in v times some vector v, this better be equal to a times in the codomain of phi of v. So if it preserves both circle plus and circle multiply, then it will be a linear map. And then obviously if it is bijective, we call it an isomorphism. And this is true for most structure-preserving maps. Now, something we can do is use the fact that every vector space has a basis, and the fact that every vector in a vector space has a basis decomposition, and I can use that to prove that we only need to know how the function acts on the basis elements. So if I do phi and I apply it to some vector v, by the decomposition of that vector in the basis, we can have the sum from I equals 1 to n of v alpha I. Notice that the alpha I is written in the superscript. That's going to be important later. Scalar multiply in the domain of e alpha I. By the fact that phi is linear and it preserves summation and scalar multiplication, I can move this sigma and this scalar multiplication outside. So I can have the sum from I equals 1 to n of v alpha I scalar multiply in the codomain of phi applied to e alpha I. Now this right here looks very, very nice. And so what we define is that this right here is called phi sub alpha I. And this is the reason why I wrote the components of a vector in the superscript, is because these components are written in the subscript in order to correspond with the subscript of the basis. These are called the components of the linear map. It's just phi applied to e alpha I. And so what we can instead define is if I know the phi alpha i's, then I can construct the linear map back from it. So I can define phi of v to be the summation from I equals 1 to n of v alpha I scalar multiply phi alpha I. And so it acts as a sort of alternative basis, although it isn't really a basis. So if we only start off with the knowledge of the components, we can uniquely determine a brand new operation. And of course, this is scalar multiplication in the domain. Now, this right here allows us to define a new vector space, which is a Ham set. So I can define the Ham sets between two vector spaces v and w to just be the set of linear maps, phi from v to w. Alright, and we can define a vector space structure on here. So let's say I wanted to take two vectors from here, which are linear maps, say phi and psi, and I wanted to vector add them together. Well, this will give us another linear map, and so we can apply this to a vector v. What we define it to be is phi of v plus in the codomain of phi of w, which you can prove is in fact linear pretty easily. And then same thing with scalar multiplication. If I wanted to do some element of the field, scalar multiply a linear map phi, I apply this to some vector, and I define it to just be a scalar multiply on the codomain of phi applied to v. Pretty easy to define a vector space structure on here. So now let's look back to our first example of a vector space, which is the field itself. Now let's define what is known as a dual vector space. And it's simply going to be the vector space of the linear maps between v and the underlying field. So this is a vector space over this field. Now we can actually define a basis on here. Let's define epsilon alpha. And by the fact that we only need to know its components, I can just do epsilon alpha applied to a basis element on the vector space. And I'll say that this is equal to 1 if alpha is equal to beta, and it's going to be 0 otherwise. 1 is the multiplicative identity on k, and 0 is the additive identity on k. And using this fact, let's go ahead and write out what it is applied to a general vector v. So epsilon alpha applied to v is the sum from I equals 1 to n of v alpha I scalar multiply epsilon alpha applied to e alpha I. Now note that scalar multiplication is in the codomain, and so it really is just field multiplication. By the definition, whenever alpha is not alpha I, that means that it's going to be 0. And so this entire term is going to be 0, except when alpha is equal to alpha I, it's going to be 1. And when you multiply something by 1, you just get v alpha. So in the alpha component of this vector decomposition, it will be the only non-zero component. And so the only thing that won't just be 0 will be v alpha, the alpha component of v. And note that if alpha I is never alpha, so that alpha I and alpha are distinct, it's going to be 0 by this alternative definition of the components. Well, isn't that really nice? The cobasis applied to a vector retrieves a single component of that vector. And that's very useful for when we're trying to figure out the components of vectors, because you just say, do the cobasis applied to it. Now we can use this fact to prove that epsilon alpha is in fact a basis. So let's say we have some general phi. This is just some element of the dual vector space. And I can apply this to some vector v. By this fact, this is equal to the sum from I equals 1 to n of v alpha I, scalar multiply, but we're in the field, so it's just normal multiplication, of phi applying to e alpha I. Wouldn't you look at that? V alpha I, we have a method for getting this from the original vector. And it's just applying the cobasis. So this is really equal to the sum from I equals 1 to n of the cobasis epsilon alpha I applied to v by this fact right here. And then we multiply in the field of phi of e alpha I. Now we use the definition of the components of phi, and we write that this is equal to the sum from I equals 1 to n of phi alpha I times epsilon alpha I applied to v. Now that looks exactly like a basis. Right here is a map, right here is an element of the field. This is like a linear combination of the basis elements. So by this fact, we have it that phi is equal to the sum from I equals 1 to n of phi alpha I, linear map multiplication, epsilon alpha I. The beautiful relationship between the basis and cobasis is that if I have a covector and I apply that to a basis element, I get that component of the covector. And if I do a cobasis element and I apply that to a vector, I just get that component of that vector. And so there's this great relationship between the cobasis and basis that is really helpful when doing math. Now I did oversimplify this a tiny bit in that this may not be a finite sum, but it's pretty much a basis. So we can just assume this. Now let's go ahead and take a look at tensors, given all of this information that were needed as prerequisites. A tensor is going to be a linear map, and it will be from the Cartesian product of the dual vector space with itself, say p times, and then it will Cartesian product that with the Cartesian product of the vector space with itself, say q times. And then it will output this, and it will take that to some element of the field k. So if this is a linear map, we call this a PQ tensor. So P is the copies of the dual vector space, and Q is the copies of the vector space. So let's do an example of a 1-1 tensor. We will have a linear map which takes in one covector and one vector and outputs an element of the field. So we do T, and we can input a covector phi and a vector v. And that will be a 1-1 tensor. Now what we can define on any general PQ tensor is what are known as the tensor components. So if I do T, and for the first P slots, I input cobasis elements. So I have epsilon alpha 1 all the way up until epsilon alpha p. And for the next Q inputs, I input basis elements. So E beta 1 all the way up until E beta Q. And this will define the tensor component T. On the top, I'll have alpha 1, to alpha p, and on the bottom I'll have beta 1 to beta q. And this was the purpose of writing the cobasis components and the basis components with different indices, so that we can have superscripts for the cobasis and subscripts for the basis in tensor components. Alright, now let's go ahead and use tensor components and use these tensor components to define the tensor in general. So let's go ahead and do T, and we apply it to a bunch of covectors, say phi1 up until phi p. And notice that I wrote it in the superscript so that I can write the components. And then for the vectors, I'll input v1 up until vq. By the vector decomposition of both of these, this is going to be equal to T of a sum from I equals 1 to n of phi1 alpha I, scalar multiply epsilon alpha I, and then sum from I equals 1 to n of phi2 alpha I, scalar multiply epsilon alpha I, all the way up until the sum from I equals 1 to n of phi p alpha I, scalar multiply epsilon alpha I. And then for the vector components, we'll have the sum from I equals 1 to n of v1 alpha I, scalar multiply e alpha I, all the way up until the sum from I equals 1 to n of vq alpha I, scalar multiply e alpha I. And please note that this scalar multiplication on the normal vectors. Alright, now note that this scalar multiplication is different from this scalar multiplication, although they are very, very similar. Now by linearity of t, I can pull out all of those summations. So I'll have the sum from I, let's call it I1 equals 1 to n, all the way up until the sum of I, let's call it p equals 1 to n. So these summations are for the p inputs for the covectors. Now let's go ahead and do the sum of j1 equals 1 to n, all the way up until the summation of jq equals 1 to n. Now these q summations are for the q inputs of vectors. Now let's go ahead and write out all the components. So we will have phi1 alpha I1, so this is for the first indice, multiply that by phi2 alpha I2, all the way up until phi p alpha IP. And then we'll multiply that by the vector components, which is phi1 alpha j1, all the way up until vq alpha jq. And then we'll multiply this by what is left, which is all of the cobasis elements and basis elements. So this is epsilon alpha I1 up until epsilon alpha IP, and then I'll have E alpha J1 up until E alpha JQ. And this right here, very clearly from the definition, is just the tensor component. So we can replace this with T. The superscripts are going to be the cobasis components, so that's alpha I1 up until alpha IP. And then in the bottom, we're going to have the vector components, which is alpha J1 up until alpha JQ. Now please note that I assumed that all these n's are the same and all the indices are the same, just for the sake of not having to write different n's on the top. And the reason I'm allowed to do that is because I could just add in a bunch of zero components in order to make up for any lost indices. So given a tensor, you have all of the components multiplied together, multiplied by the tensor. And the way we usually represent this is not by this, it's instead by removing the summation. And this is another use for writing the indices like this. So let's go ahead and write phi1 alpha I1 all the way up until phi p alpha IP times v1 alpha j1 all the way up until vq q alpha j q. And we multiply this by the tensor component, which is alpha I1 up until alpha IP, and then on the bottom alpha J1 up until alpha JQ. And then the way the summation is still sort of there is by this Einstein summation convention. Right here we have alpha I1 to alpha IP in the subscript. Right here we have alpha I1 to alpha IP in the superscript. The Einstein summation convention says that because there's one in the subscript and one in the superscript, we sum over that. So every time you see something like that, we add in a summation for it. And then same thing here. Right here it's in the superscript, right here it's in the subscript. Einstein summation convention says that we sum like that. So let's go ahead and write out a vector. So v is equal to the sum from I equals 1 to n of v alpha I, scalar multiply e alpha I. By the Einstein summation convention, we can just write v alpha I, scalar multiply e alpha I, and the summation is implied because we have one in the superscript and one in the subscript. That's how the Einstein summation convention works. If there's an index in the superscript and that same index in the subscript somewhere else, you sum over it. And so this allows us to write in slightly more simple terms. Alright, let's do an example of a 1-1 tensor. So if I want to do t applied to phi and v, this is going to be equal to phi alpha times v beta times the tensor component alpha beta under summation. So right there is the Einstein summation convention. Well, that's actually extremely simple, and that's why we have the Einstein summation convention, so that we don't have to write out all those pesky summation signs. And that's it.